Our everyday definition of acceleration is how quickly something speeds up. Also important is how quickly it slows down, but you might call that deceleration. But mathematically, we just care about mathematically, you could define the average acceleration as the change in the velocity, delta v, over delta t. To get a little more specific, you know that for averages it's always a period of time, and you just care about the initial and the final. So you could say it's the final velocity minus the initial velocity over delta t, where those are instantaneous velocities at those times. You can also define an instantaneous acceleration, and that would just be the derivative of the velocity with respect to time. Or if you had a velocity time graph, it would just be the slope of the velocity time graph at a certain time, because it's instantaneous. So these probably look familiar because mathematically it's exactly the same as talking about the average velocity and the instantaneous velocity and how those depended on position. Now we've just moved down the level and we're talking about the average acceleration and the instantaneous acceleration and how they depend on velocity. But mathematically looks very similar. If the acceleration is constant, then you have the case where the average equals the instantaneous. Just like earlier when we had uniform motion, we called it uniform if the velocity was constant. In that case, if you had some interval and got the average velocity or you got the instantaneous velocity, they were always the same. Well, they're always the same here as well if the acceleration is constant. And in almost all the problems you're going to do in introductory physics, the acceleration will be constant. For the acceleration to change is an effect called jerk, and we don't put up with jerks in freshman physics, so it's always going to be the case that accelerations are constant. You may also wonder, where's the other two? Where's the speed equivalent? Well, there isn't really a speed equivalent at this point. We always think of acceleration as a vector. We have no use for just the magnitude, so we won't worry about that. It's really just these two. I said I wouldn't do any demos in this YouTube channel, but here's one. I'm going to take a piece of chalk and drop it, and we just made it accelerate. So let's have a quick look at the kinematic plots for that. Let's see, if we were going to plot, I'll plot the position x, and I'll plot x down like that. So this will be minus x, and this will be time. If you were to plot that, it will look kind of like this. It started, and it went down like that. You could also plot the velocity minus v, and you know that's the slope of this line. So you can see it had zero slope there, dx dt, and then it got an increasing negative slope. It actually would come out straight like that. And finally, you could also plot the acceleration, which is the slope of the velocity, like this. And I haven't left myself a lot of room, but I don't need it. Here's the minus acceleration, and you can see, since that slope is constant, it would just look like this. So when you drop something, it has a negative acceleration. Maybe you know why, if you've had a little bit of physics. We'll be getting to that soon. But let's look. Let's just define our two values here, just to make sure you know what to do with them. The average velocity, say between, let's calculate it between 0.1 seconds and 0.2 seconds. And those 2 points right there. So we could bring it all the way down like this and say, okay. Then the average velocity would be, we would just get the actual slope or the velocity reading right there at 0.2 minus the velocity at 0.1 and divide it by 0.2 seconds minus 0.1 second. If you really wanted to do it exactly, that's what you would do. And if I did all this with proper units and did a slow motion analysis of the video, I guarantee you I would get that it's minus 9.8 meters per second squared in the I hat direction down along the x-axis. Because as you know, this is gravity, and we know the acceleration due to gravity. We'll get into that later. If I said, let's find the instantaneous value, then if I plotted all these perfectly numerically with all the units relevant, blah, 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 and I took the slope of this line, I know I would get minus 9.8. meters per second squared. Negative on the I-hat direction on the x-axis. And I know they would be the same in this case. Any interval you do, they're going to be the same because we have the case of constant acceleration.